Cross products versus dot products. Moments R cross F versus work, force through a distance. Okay, so cross products, let's just compare these two for a second. If I have some kind of an axis of rotation, right, and a position vector and a force, and I'm going to say moment is equal to R cross F. And we'll split the position vector into XY components. And then we'll split the force into its XY components. Maybe it's a two-dimensional. And then we'll go through this. And this will get us three different directions, right? It's going to give us how much is twisting around the X, the Y, the Z axis, and then the total moment is going to be some combination of the X, the Y, and the Z. So it's a vector, just like force is a vector, just like this position vector is a vector. So you have, some kind of a moment, and that moment is a vector that's describing the axis of rotation, and that the moment vector, you can split it up into X and Y and Z components for however this thing is moving around, right? So just like you can split a force into X, Y, Z components. The point of a cross product is to figure out, if I take this force and divide it up into how much of that force is in the same direction as this R versus how much of that force is perpendicular to it. So for a moment, you're looking for the perpendicular piece of those two vectors. There's a different way. So you can walk through the cross product, or if I know this angle, then the opposite side, this moment, you could also say is equal to the position vector times F sine theta. That would get me the exact same thing as this cross product would give me. But it's going to be something that has direction. Okay, so that would be a magnitude, but then I'd have to look at my diagram and realize kind of what axis it's rotating around and what direction is going on. For dot products, and let me just give myself some room here. We're going to start with a similar situation. So let's start with two vectors, and we can call it R cross F, or just two different vectors, right? So maybe here's one vector and here's another vector. And the difference between a dot product is, instead of getting this normal piece, we are instead going to get the part of the vector that is in the same direction. And this would be for applications like work. So when you say, let's have a box, and you're pulling the box across some surface, right? And maybe it moves a distance delta x, and we say, how much work did that take, if you remember from physics? So for physics, you would have to break this force into how much of that force is in the same direction as the displacement, and then the work would be that F cosine theta, right? It's in the adjacent piece of it, times the displacement. Okay, so the perpendicular piece of the vector versus which piece of it is in the same direction. That is what a cross product is. Another use for cross product is, well, I'll do this for the next video, but if I have something like this, let me just zoom in here. Maybe I don't want the the moment around the X or the Y or the Z direction. Maybe I want the moment around some other direction. And what I can do is, if I know what direction I'm interested in, I can use the dot product to figure out, oh, how much of this vector is going here. So it's just these, the normal and tangent components, breaking vectors into normal and tangent components is a very common thing that you'll see in a lot of different applications and vector problems. How to set this up, and I will post a video that derives this equation. It comes from the law of cosines. But basically, to get this vector times that vector to see how much is in the same direction, and then you're multiplying them by one another, what you're going to do is take x times x, y times y, z times z. So let's say you have some vector AB, and that vector has x, y, z components. What we would do here is we would take the x component of the AB vector, multiply by the x component of this other vector, and then you add the y component of the first vector times the y component of the next vector, and then you add the z component of this vector times the z component of that second vector. So that's what's happening here. It's x times x plus y times y plus z times z. Something to notice about this dot product, it is a scalar property. This is not a vector anymore. It is just a magnitude. So like work is not a vector. It is just a magnitude. It's not a direction. It's not up or down. So that is a little bit different than, you can see these vectors and you can see which direction they're in, draw a picture of it, but when you crank through the dot product, it's just a magnitude. On the other side of this, and you kind of saw that we're looking, if I have the angle between these vectors, I am now looking at the adjacent side, so we're dealing with cosine instead of sine. Sometimes you use a dot product just to find the angle of something. So over here on the other side of the equation, this is actually the magnitude of that vector and the magnitude of that vector, and this is the angle between them. So what this is saying right here, this would be equal to the magnitude, so this is the x component squared and the y component squared and the z component squared. If you remember how to get the magnitude, the total length of that vector, it's kind of like a squared plus b squared equals c squared, only have to add that other distance to it. And then we would do the same thing for c. So we're looking at the x component of c squared and then the y component of c squared and the z component of c squared, and we're going to take those two magnitudes and multiply them by one another. And then the cosine of the angle, we can do this dot product divided by these magnitudes multiplied by one another. Okay, so I set up a little table in Excel to do this, and here's something similar to what's in your homework. I'm going to just pull this off of two different tables than what your homework is asking for. What we want to do here is, let's say that I have dimensions of this thing and I want to figure out the angle between AB and AC. So this is some kind of crazy. If I was going to try and make triangles out of this and figure out what that angle is, that would be pretty tough to figure that out. Okay, so I'm going to split AB into its x, y, z components, and then we'll split AC into x, y, z components. You can see that C is coming just straight down the pole and straight forward. So let's do that. Let's get the x, y, z components, and then we will crank through this dot product. Okay, AB, if you see the x direction here, we're going from the origin backwards. So that'll be negative 6.5 feet. And then in the y direction, we're coming down that pole that is 8 feet tall. And the Z direction, we're coming forward. You have to really squint. So that 2 feet goes with these 2 little arrows here. So that is pegged out 2 feet in the Z direction. And we don't just need X times X, Y times Y. We're also going to need the total length of this thing. So let's go ahead and get the length. So square root of dx squared plus dy squared plus dz squared. Okay, so now we have AB broken into XYZ components and the total length. Let's do the same thing for AC, and we're drawing this vector from the side where the angle is down to the end. Okay, so in this case, there's nothing in the X direction. It's just coming straight down that same pole that's 8 feet tall. And the Z direction, it looks like we're coming forward 6 feet. And I can just take that A squared plus B squared plus C squared equation and pull it on over. Okay, so this side of the dot product, I'm going to get the dot product by saying X times X, and then Y times Y, Z times Z. And this time, we're not squaring it or anything. You just add them together. So the X times X plus Y times Y plus Z times Z. So no squaring, nothing, just add them straight together. And this is a magnitude of, it's a dot product. Okay, I'm going to grab this little piece of it. So this is the length of one multiplied by the length of the other. So there's the length of AB times the length of AC. And the final piece of this is I want to get this angle. So the angle is going to be the dot product divided by the magnitudes multiplied by one another. So I'll say, turn these into degrees, a cosine, and I'm looking at the magnitude of the dot products divided by the magnitude of these two guys multiplied by one another. Okay, so that would be the angle between those two vectors. So sometimes a dot product, you don't use it to find work, you don't use it to find a vector in some direction. You're just trying to get the angle between something, and this can be a lot easier way to find that angle.